Hello, George Romanic here. Today we are going to look into perfectly elastic collisions in the center of mass reference frame. Question number 1, what are elastic collisions? Question number 2, what is a center of mass? And then maybe even question number 3, what is reference frame? Well, we can answer question number 3, that's trivial, and I have even videos on that. Reference frame is something that we use to measure velocities, distances, and so on. It's a coordinate system. Question number 1. What is a perfectly elastic collision? Well, I also discussed that in my videos on elastic collisions. It's a collision during which total kinetic energy of the system does not change. For example, we have two particles coming in, they collide, they bounce off. Kinetic energy before collision is equal kinetic energy after the collision. That doesn't have to be the case. We discussed that. We can have particles coming in, colliding and sticking together, either not moving or continuing to move at some velocity. That would be inelastic collision. Some part of the kinetic energy is transferred into potential energy, vibrational energy, and so on. And the last question, what is a center of mass? Well, center of mass is a point, an imaginary point that behaves as if the entire mass of the system is concentrated, is put into that point. Now, center of mass can be defined for a rigid, solid body, for a liquid substance, as well as for a gas. So, if I take my infamous experimental platform and we put it over here, although in this series of videos we are particularly interested in gases, kinetic theory of gases, we can use this wooden block to also demonstrate the concept of the center of mass in the following way. I told you that the center of mass is a point that behaves as entire mass of this wooden block, in this case, is concentrated in that point. But I think more intuitive, easier definition is the following. Center of mass is the point with the following property. If you apply a force that goes through the center of mass, there is no net torque, there is no rotational motion exerted by the object. For example, if I have this wooden block over here, I apply force over here on this end. Clearly, there is torque. I am rotating this wooden block. That means I am not applying this force through the center of mass of this object. If I go closer, I go here, I apply force here, I am still rotating this wooden block, which means I am not going through the center of mass. I go a little bit more, I apply force here, I am still rotating it. I am not going through the center of mass. Now finally, I go somewhere here to the middle, I applied force, and I am still rotating it. Now you are watching this saying, experiment failed. Professor Romanic failed. Experiment failed. As Julius Sumner Miller famously said, experiment never fails. The physics never fails. It was me who failed to satisfy the conditions of the system to show what I wanted it to show. Why did this experiment now fail? When I push here across the center of the wooden block, there are two options. Option number 1, the center of mass of this wooden block is not in the center, and that can happen if there are density differences across this wooden block, which is possible but not very likely. But another reason why this experiment failed is because of infamous friction force. Roughness is not uniform across this experimental platform. So when I push this, now you see as I'm pushing it, there is no net torque. So clearly I am pushing it somewhere that is close to the center of mass, so I demonstrated my point. But even in this case, there is some small rotation, and that's because there are differences in roughness, therefore frictional forces across this experimental platform, so I get net torque, because maybe here it's more rough than here. If here is more rough than here, I'll get something like that. But the point is to say, if you go across the center of mass and you push something, there is only translational motion. I don't want to start this video from the beginning, because failure of an experiment is a beautiful thing in physics. Except if you maybe have a hadron collider and then the experiment is billions of dollars and you fail, then there are some consequences. But in this case, it's maybe a few dislikes on my video and nothing will happen. The Earth will continue rotating around the sun and you will come back to watch my next video. So it's all good. So, why are we interested in the collisions in the center of mass reference frame? Well, the center of mass reference frame, in one sentence, has a beautiful property. If we are looking at the collisions in this reference frame attached to the center of mass, then speeds before and after the collisions are the same. And velocity only changes the direction. So if the particle is moving like this before the collision in the center of mass reference frame, then after the collision it just reverses the direction of motion. Speed stays the same. Remember, velocity is a vector. It has speed, direction, and sense. So that is absolutely beautiful property of the center of mass coordinate system that is often used whenever possible to analyze collisions. Another beautiful property of this choice of the reference frame is the following. Whatever the center of mass was doing before the collision, it will be doing after the collision if there are no external forces affecting the system. That means, if we have two particles colliding, if the center of mass was stationary, had no velocity, it will be stationary after the collision. If the center of mass, two particles are coming in, let's say one is coming from the camera, another from my head, and they are colliding. If the center of mass was going towards you, it will continue doing that after the collision. So that's also the beauty of the center of mass of a system. Now, when we discussed all these things qualitatively, let us address it quantitatively. Let us now look into a collection of particles, say these 6 particles, 1, 2, 3, 4, 5, 6. Here is a reference system, X, Y, Z. Each of these particles has its own mass, so there are 6 masses for these 6 particles. This particle over here has a radius vector R1, so this is particle 1, 2, 3, 4, 5, 6. For example, particle 4 has radius vector, this one, R4, and so on. I don't want to plot all radius vectors because it will become too busy. Total number of particles in this case is 6. Ri is radius vector of particle I. And of course, I goes from 1 to n. Now, this system, depending on the location of these particles and their masses, has the center of mass. And let's say center of mass is right here. And this center of mass has its own radius, capital R. So this is Cm, and capital R is the radius vector of the center of mass. The center of mass is the point that satisfies this expression, that the sum over all particles from 1 to n is 6 in this case, mi times ri minus capital R equals 0. This is the definition of the center of mass. And it will be clear why this is the definition of the center of mass once we express this equation in terms of capital R. So to do that, we see from here that we can write that this is sum when I goes from 1 to n, mi ri minus R, because R is not indexed, so it can go in front of the sum. Sum goes from 1 to n, mi equals 0. Or, solving this equation for capital R gives us sum I goes from 1 to n, mi ri divided by sum of all masses, and I will call it capital M, because this is just sum of masses of all these particles. Although in this list of videos on kinetic theory of gases, we are not talking about solid body. Just as a small tangent here, I will generalize this formula for a solid body. Let's say we have some solid body over here, which is three-dimensional, of course. And now let's say the different parts of the body, this solid body, a piece of iron or a potato, have different densities. So this is density, this region has density 1, this region density 2, this is density 3, 4, and density of region 5. What is center of mass of this potato? Well, again, we define a coordinate system, let's say x, y, z over here. We take radius vectors to the center of each of these segments. So this would be again R1 and so on. This over here, last one, would be R4, right? This is getting a little bit messy, but you get the point. And the radius vector of the center of mass of this potato is simply 1 over m. Again, you see similarity, but because this is continuous body, solid body, instead of sum, we tend to use integral over, let's say, total volume of the body is q, over the total volume of this body, rho as a function of this radius vector of each density patch times r times dv. And here we use densities because you can see that density times dv will give me dm. Instead, I could use, of course, r dm, but it is difficult to determine mass of a different patch of a solid body. It's easier to determine density, and therefore this is the expression for the center of mass in terms of solid body. But in this series of videos, we are interested in discrete particles, and there are n of them, and that's the basic premise of kinetic theory of gases. Now let us develop this theory further, but we will simplify this and say that n is 2. There are only 2 particles, because if we do it for 2, most of these principles will hold if n is larger, 6 or even larger. So let us look at the system where we have 2 particles at some distance, like this. And we define some coordinate system, x, y, z. This is particle 1, it has mass m1, this is particle 2, it has mass m2. The radius vector to this particle is this, r1. The radius vector to this particle is r2. We know from the previous page, therefore, that the radius vector to the center of mass is simply m1 r1 plus m2 r2. divided by capital M, where capital M is m1 plus m2, total mass of this system. And let us assume that the center of mass is somewhere here. So this is Cm. And there is radius vector to this center of mass, and we call it this capital R that we just defined here. What I will do now is that in this center of mass I will define new coordinate system. This will become a little bit messy, but you have to stay with me, so to speak. So this is x prime, y prime, z prime coordinate system. And in this coordinate system, these two particles have different radii compared to xyz coordinate system. Namely, of course, this is r1 prime, and this is r2 prime. These are vectors also. You will notice that from figure that r1 prime is equal r1 minus capital R. Or it's easier to notice that r1, this one, is equal this one plus that one. So it's capital R plus r1 prime. And therefore r1 prime is r1, there is no prime here, is r1 minus R. Similarly, r2 prime is r2 minus capital R, because r2 is capital R plus r2 prime. Now let's continue, let's say, with this r1 prime. Instead of R, I will substitute this expression, and we will get that r1 prime is equal r1 minus m1 r1 plus m2 r2 divided by capital M. Because capital M is m1 plus m2, I will have m1 r1 plus m2 r1 minus m1 r1 and minus m2 r2. Notice that this and this will cancel and everything is divided by m. Okay, m1 plus m2. Or r1 prime is equal, m2 can be taken in front, and I will have r1 minus r2 and everything divided by m1 plus m2. This term over here is called relative position, and we usually denote it as r12, and that is r1 minus r2. So that is relative position between particle 1 and particle 2, and that would be this vector. So this vector would be r12. Notice that the relative position r21 is simply minus r12, because that would be this same vector but pointing in the opposite direction. And you can again see from vectors that r2 plus r12 is r1, which is in accordance with this equation over here. We can write, therefore, that r1 prime is equal m2 divided by the total mass of the system, r12. And similarly, of course, we could write that r2 prime is equal minus, because we will have r21, m1 divided by m R12. These are position vectors in the center of mass frame. And we express them in terms of the masses and the relative position vector between two particles. What is extremely important to know is that relative position vectors, such as this one, do not depend on the choice of reference system. We can use laboratory reference frame or center of mass reference frame or some other laboratory reference frame, somewhere here, let's say. These relative position vectors, as well as relative velocities, as we will see later, do not depend on the choice of reference system. Positions depend, but not relative positions. So the next question is, what is the velocity of the center of mass? Well, we found that radius vector of the center of mass is m1 r1 plus m2 r2 for these two particles above that I analyzed, divided by m1 plus m2. Well, that means that velocity of the center of mass is simply dr dt, and therefore that is equal m1 v1 plus m2 v2 divided by m1 plus m2. So if we go back to our figure over here, that means we can have velocities of these two particles. Let's say this is v2, and over here we have v1. I hope you can see v1, v2. This is becoming very busy graph, but what can you do? If you are following me, it's quite simple. So knowing these velocities and masses of these particles, we can determine the velocity of the center of mass, which is also a vector, by the way. Further, let us calculate the velocity of these two particles in the center of mass reference frame, because velocities v1 and v2 are velocities in this laboratory reference frame. But what we are interested is these velocities in the center of mass reference frame, because we will see something remarkable when it comes to center of mass reference frame. v1 prime, and the prime was used for the center of mass reference frame, is equal dr1 prime dt. But r1 prime is this, so we get that this is equal m2 divided by capital M. Derivative of this is simply v12, where, of course, you must know now that v12 is v1 minus v2, which is a very important concept, and that is relative velocity of these two particles. And just like in the case of radius vector, v21 is equal negative v12. Speeds of relative velocities measured in respect to 2 and 1 particles are the same, but directions are reversed. That's what this equation says. Similarly, v2 prime is equal dr2 prime dt, and that is equal minus m1 divided by capital M v12. So now we know radii in the center of mass reference frame, and we also know velocities in the center of mass reference frame. Now let us look into the collision of two particles. Here is particle with the mass m1. It is moving in this direction and it has velocity v1 initial, And here, let's say, is particle that has mass m2, and it is moving in this direction with the velocity v2 initial. Because this is one-dimensional case, we don't even need to use vectors, and we will omit vectors hereafter. So this is before collision. Now, after collision, as we saw in my video on elastic collisions, maybe collision happened somewhere here, and now this particle m1, these circles should be the same size, but this particle m1 is maybe moving in this direction with velocity v1 final, and this particle is moving in this direction with velocity v2 final. Before collision, we have that the relative velocity v12 initial is equal v1 initial minus v2 initial. If you want, you can add vectors, of course, but because this is 1D case, in principle there is no need. At any rate, relative velocity after the collision, where I stands for initial, F stands for final, is equal v1 final minus v2 final. And again, if you want, you can add vectors. Relative quantities are independent of the reference frame, so these relative velocities should be the same regardless of the reference frame that we are using to analyze this collision. Let us look into the analysis from the laboratory reference frame. We saw that v1 final in the laboratory reference frame was m1 minus m2 divided by m1 plus m2 v1 initial plus 2 m2 m1 plus m2 v2 initial. We saw that in my previous video on elastic collisions. And we also saw that v2 final, this one, is equal to m1 divided m1 plus m2 v1 initial plus m2 minus m1 divided m1 plus m2 v2 initial. So what is v1 2 final? Well, that will be v1 final minus v2 final. So notice that I can factor terms around v1 initial, so that will be m1 minus m2 minus 2m1 divided m1 plus m2 v1 initial plus 2m2 minus m2 plus m1 divided m1 plus m2 times v2 initial. But notice that this will cancel with this over here, because this will be m2 plus m1 with the negative sign in front. So what I'm saying, this will become v12f is equal negative, this is 1, v1 initial plus. Similarly, this of course cancels with this, and we get v2 initial. But this over here is, you will notice, simply minus v12 initial. So the big revelation from this derivation is that v12 final is equal minus v12 initial. Relative velocities after the collision are the same as relative velocities before the collision, but with the sign of the direction switched. or, if you wish, relative speeds after the collision and before the collision are the same. We saw on the previous page, we just derived it, that v1 initial prime, so this is velocity of particle 1 in the center of mass reference frame, is equal m2 divided by capital M times v1 2 initial, and we also had that v2 initial is equal negative m1 divided by m capital M, or m1 plus m2, whatever, v12 initial. So this is initial velocity of particle 2 in the center of mass reference frame, and this is initial velocity of particle 1 in the center of mass reference frame. But we also found that relative velocities before and after the collision are the same up to the sign, and this is irrespective of the reference frame, because we used the laboratory reference frame here. So when we combine these two, we can see that in the center of mass reference frame, velocity of particle 1 after the collision is equal negative velocity of particle 1 before the collision. Velocity of particle 2 before the collision is equal negative velocity of particle 2 after the collision. While relative velocities before and after the collisions are the same regardless of the reference frame, it is only for the center of mass reference frame that velocities before and after the collisions are the same up to the sign. Not relative, but absolute speeds in the center of mass reference frame are the same before and after the collision. The next thing that is very important to realize that the behavior of the center of mass is the same throughout the process of collision. So in this case, whatever the center of mass was doing before the collision, it will be doing during the collision, and it will be doing after the collision. If the velocity of the center of mass was 0 before collision, it will be 0 during and after the collision. If the velocity of the center of mass was 5 meters per second before collision, it will be the same during and after the collision. And to make this video even longer, I would like to demonstrate that. Let us say that here at time t equals 0, we have this reference frame x, y, z. We have in the y, so this is positive y direction, as you can see. We have particle 1 over here with the mass m, let's call it mass m, and it is moving in this direction with the velocity, let's say v1 is 9 meters per second. The distance of this particle from the origin is, let's say, 1 meter. Somewhere over here, we have another particle that is standing still. It has mass 5 times this particle, 5m. But velocity v2 is 0. So this would be v1 initial, v2 initial. The distance of this second particle is 10 meters from the origin. So clearly, after some time, and that is basically 1 second, there will be collision between particle 1 and particle 2. Why 1 second? Because I set up this problem to be convenient. As you can see, it's 9 meters between particles 1 and 2. And velocity of particle 1 is 9 meters per second, so in 1 second 9 meters will be traversed, and there will be collision between these two particles. What is the distance of the center of mass? Well, r is equal m1, which is m, times the distance, which is 1 meter, plus m2, which is 5m, times the distance, which is 10 meters, times 10 meters, divided by 5 plus 1, 6m. And if you calculate this, you will get 8.5 meters. So the center of mass is somewhere, let's say, here. (8.5 meters). Now, what is the velocity of the center of mass? Well, velocity of the center of mass, and I will say initial, before collision, is equal m1, that is m, times velocity of particle 1, which is 9 meters per second, plus 5m, velocity of particle 2, that's 0, divided by 6m. And that is equal, this over here is 0, so it gets m and m cancels, 9 divided by 6 basically. And that is equal 1.5 meters per second. Now, in 1 second, as I just said, these two particles will collide. Now let's see what's happening 2 seconds after this time. So collision already happened. We can calculate velocity of particle 1 after the collision using equations from the previous slide. m1 minus m2. So that would be m minus 5m divided by m plus 5m times initial velocity of particle 1, which is 9 meters per second, and plus 0, because the second term is proportional to initial velocity of particle 2, which is 0. So if you calculate this, you will get minus 6 meters per second. So we see at time t equals 0, at time t equal 2 seconds later, particle 1 will bounce off with the velocity of minus 6 meters per second, and particle 2 well, we need to calculate for particle 2. Let's do it here to save space. Final velocity of particle 2 is equal to m1, that is 2m, divided by m1 plus m2, that is 6m, m and m cancels, times v1 initial, that is 9, and again plus 0, because the second term is proportional to v2i, which is 0. So if you calculate this, you will get 3 meters per second. So particle 2 moves in the positive y direction with velocity of 3 meters per second. Now is the punchline. And there are two of them. Well, first, notice that the relative velocity is still the same. 9 minus 0 is 9. Minus 6 minus 3 is minus 9. So speed is the same. Direction of the relative velocity is different. And that's exactly what we demonstrated on the previous page. So that's punchline number 1. Punchline number 2 is what is velocity of the center of mass after the collision, final. Well, that is m1, which is m, times minus 6 plus m2, which is 5m, times velocity 2, which is 3 meters per second, divided by 6m. Again, all these masses cancel, and velocity of the center of mass after the collision is equal. So 3 times 5 is 15 minus 6 is 9 divided by 6. But that's exactly what we had here. And that is therefore equal 1.5 meters per second. What did we conclude here? Well, while there was collision in these 2 seconds, absolute velocities changed. This was 9, this was 0. Now it's minus 6, 3. Relative velocities changed only direction, speeds stayed the same. Center of mass didn't do anything. It behaved the same way as before. The velocity of the center of mass is continuously in this direction, v center of mass, and it is 1.5 meters per second, and it will stay forever as these 2 particles are now coasting in the opposite direction from each other. We are at the Collision Lab website. I will put the link in the description so you can explore it on your own. I set up a simple experiment that will show that the center of mass before and after the collision is the same. We have particle 2 and particle 1. Speeds of these 2 particles, as you can see, are the same, and they have opposite directions, which means they will collide. Here are their momenta, which is not so important, but of course momenta are also the same. Kinetic energy of the system is 1.19 joules. When I start this simulation, kinetic energy will stay unchanged. The particles will come in, collide, and then bounce off, but the center of mass will do nothing. We can repeat the experiment, and you can see that in perfectly elastic collisions, kinetic energy is the same, and the center of mass is always unchanged. We can change something, for example, velocity, decrease velocity of this one. Now the center of mass will be moving, but the speed of the center of mass, 0.28 meters per second, will be the same before and after the collision. Look. It is just coasting forever with 0.28 meters per second. We can repeat the experiment for even smaller value of velocity of particle 2. The center of mass is moving at the constant velocity before and after the collision. And we can increase the number of particles, and you will observe the same. Let us just maybe increase the mass of particle 1 so we move center of mass in this direction, and let us see what will happen now. Notice how the center of mass is coasting at the same speed forever before and after the collisions. This was very nice setup, so let's repeat it. 0.20 particles collided and the center of mass continues. In our next video, we will define the concept of temperature in the framework of kinetic theory of gases. And this video, where we looked into collisions in the center of mass reference frame, will be one of the main themes in the definition of temperature of a gas. Until next video, goodbye.